All right, welcome to a quick video on limits with piecewise functions. There's going to be quite a few of these problems on your tests, and a lot of kids have a tendency to maybe misunderstand them or mess them up a little bit, so I want to take a look at a couple. All right, so here's a function. Remember, I've tried my best to teach you that the first thing you need to do when you approach any kind of problem, especially a limit problem, is you got to ask yourself, what the heck's going on? What's this problem asking me about, and where are my discontinuities at? Because where you have discontinuities is where there's going to be problems. So if I see a function like this, typically I realize right away that there is a number, x equals -5, that makes the denominator 0. But that could be one of two different types of discontinuities. So I guess I need to factor the top and see what's going to happen up there as well. And if I factor the top, let's see here, I'm going to need a 5, I'm going to need a 3 to get that 15. Looks like I want a +5 and a -3 and to work out that correct factoring. Now this allows me to instantly see that -5 is a removable discontinuity, which means there's a hole. And to find out where that hole is, all I got to do is remove those x plus 5s, and all that's left is x minus 3. So now if I plug -5 into what's left over, I get -8. So that means that the hole is located at -5, -8. So that's where the hole is at. Now, that's a point. I just wrote down a point. But that's not a point on the graph. That is the point that is missing. So if I would like this function to become continuous, I would need to fill that point in with -5, -8. That's the missing point. If I fill it in with that point, then I will be continuous. Now the only way to make this happen is with a piecewise function. So if I have a piecewise function that has x squared plus 2x minus 15, all divided by x plus 5. Now, this function will only work if x does not equal -5, because remember, there's a hole at -5. If x does equal -5, what value, I'll just call it k for right now, what value do I have to put here to fill in that hole? Because the function on top here is a great function. It's continuous everywhere except for -5. So if I want this piecewise function to be continuous everywhere at -5, when x equals -5, I have to fill that in. And what do I fill it in with? Well, where the hole is at. That would be -8. So if my k value was -8, then this would work out. This would be a good function that is continuous everywhere. So if I fill this in, do that real quick, with -8, basically I'm making this function become continuous, because this top graph is a great graph, right? But it has a problem at -5. So if I fill that in with -8, then I'm good to go. Now, what else could happen? Now, what's another type of question I could ask you? Well, I could do something like this. I could say x plus b. And I could say, okay, to make this continuous, what does b have to be? Well, this time, I still need this to be -8, right? I mean, because that's the only way that this is going to fill in that hole. The only way for this to become continuous is if that hole gets filled in. So I still need x plus b to be -8. Again, where am I getting -8 from? Remember, once I removed that x plus 5, my discontinuity, I was able to be left with x minus 3. And if I replug -5 into that, that's where I'm getting -8 from. So now if I ask myself, okay, x plus b is more than just a number, right? If I wanted just a number, it would need to be -8. But now it's x plus b. There's an x in there, but I still need that value to be -8. So what does b have to be? Well, let me add that 8 over, and x would have to be -5, because again, x is -5, right? That's what this says right here, and that's where the hole is at. So again, I got to remember x is -5, so if I fill in the x with -5, plus b equals -8, well then now I could solve for b. So all I got to do is add that 5 over, and I get -3. And now if you go back and think about this, just makes complete sense. If I were to replace solve this with x minus 3. Now, when I plug in -5, which I'm not allowed to do up here, so that's why I got to go down here. If I plug in -5, -5 minus 3 is negative 8. So that will fill that hole in at negative 5. I'm negative 8, and that will create me to become continuous. So again, there's several different ways I can ask this question, but you have to understand where's that hole at, because I need it to be filled in. Now, x minus 3 is a line, and a line has a million, quadrillion, infinite points. Well, the only point I need from that line is negative 5, negative 8. I just need that one point to fill that hole in. So that's what you got to kind of think about for a piecewise function like that. Now again, all by itself, this function is not continuous at negative 5. But if I make it a piecewise function, I can fill that hole in, thus making it continuous. All right, let's look at another one here. This is another function, and it tells us when x is less than 5, we're going to use the function 3x squared minus 7x. When x is greater than 5, we're going to use the function 2x plus b. And the question is, what does b need to be in order for this to be continuous? Well, the key is the transition point of 5. When I plug 5 in, I need to get the same value when I'm less than 5, that's to the left, as when I'm greater than 5, that's to the right. So if I plug in 5, I get 3 times 5 squared minus 7 times 5. And when I plug in 5 to the bottom, I get 2 times 5 plus b. And if I'm going to be continuous at 5, then I need these two values to be equal. I need them to come together. Therefore, the limit does exist. So again, all I got to do now is solve. This is like the easiest equation to solve for. 5 squared is 25. 25 times 3 is 75. Minus 35 equals 10 plus b. 75 minus 35 is 40. Equals 10 plus b. Subtract the 10, and 30 equals b. So if this is 2x plus 30, when I approach 5 from lower than 5 or above 5, greater than, less than, left, right? When I approach 5, I'm going to get the same value, making it continuous. And that's the important part. And what value would that be? Well, that'd be 40. Because when I plug 5 into the top, I get 40. When I plug 5 into here, I also get 40. And that means that my graph is coming together at 40. Thus, I will be continuous. So again, really easy problem. You just got to understand that idea. All right, and here's another one. Okay, this is kind of like that first one we looked at. And we're simply saying, okay, we have this top function here, x squared plus 7x plus 12, all divided by b, some constant, times x plus 3. And as long as x does not equal negative 3, I'm going to use that function. That actually makes complete sense. But let's make sure it really makes sense. Because I need to factor that top. Because there is a difference between removable and non-removable discontinuities. So I need to make sure that this is a whole. And of course it is. If I factor the top, I also get an x plus 3 factor. Those factors could be removed, and all that's left would be x plus 4 over b. And that tells me that there's a hole at negative 3. There's a hole at negative 3. And all I got to do is fill that hole in. Well, what do I fill that hole in with? Well, if I fill that hole in with b, the missing value, then I'll be continuous. So now all I got to do is I got to plug in negative 3 for x, and I got to solve for b. All right, for the top function, I'm only going to plug in negative 3 after I get those factors to cancel. Because if I plug in negative 3 beforehand, I'm just going to get a double zero. So let's see here. I get negative 3 plus 4 over b, and I need that to equal b, because I need the top to equal the bottom at negative 3. So I plug negative 3 in to the top, plug negative 3 into the bottom, which there was nowhere to plug it in for, and I now need to make sure these are equal. Well, let's see if we can solve this. Negative 3 plus 4 is 1. Multiply the b over, and I get b squared. Take the square root of both sides, and I get positive or negative 1 equals b. So if I replace the b right here and right here with either positive or negative 1, I will force these two functions to match up at negative 3 and fill in that hole, because there is a hole, and all I got to do is fill that hole in to make it continuous. So when you have these piecewise functions, the transition points are the most important, because if you want to be continuous, if you want the limit to exist, then at those transition points you need to equal, right? So all I got to do is plug in x to both of them and solve for the value that's going to help you become equal. Not that hard, but a lot of kids do get confused on these. All right, and the only other type of problem I'd like to briefly go over is one of these double fraction problems, because I remember when we did the homework there was tons and tons and tons of questions about them, and I really want to make sure everybody fully understands how to do these problems. So we have the function 1 over 2x plus 5 minus 1/11 all divided by x minus 3. So first thing you should always do when you evaluate a limit is plug it in, plug it in, plug it in. So if I plug in 3, I get 2 times 3 is 6, 6 plus 5 is 11. Well, 1/11 minus 1/11 is 0. And in the denominator, I also get 3 minus 3, which is 0. So I do get the 0 over 0, which means that I have a removable discontinuity. And the only way I can figure out what it is if I get something to cancel. That way I can re-evaluate my limit. So here I go. I'm going to rewrite the top as 1 over 2x plus 5 minus 1/11. And instead of dividing by x minus 3, I'm going to multiply by the reciprocal 1 over x minus 3. All right, now I'm going to follow the order of operations and do the inside the parentheses first by combining these two fractions together. My common denominator is going to be 11 times 2x plus 5. This guy needs the 11 on top and bottom, so I'll multiply 1 by 11 on top and get 11. This guy needs the 2x plus 5 on the top and the bottom, so I'll go ahead and multiply the top and I'll get negative 2x minus 5, because you got to distribute the negative. Be careful, there's a negative right here, so it's going to be negative 2x, negative 5. And then I'm going to also multiply this by 1 over x minus 3. All right, so on top, let's see here, I get negative 2x, 11 minus 5. 11 minus 5 is 6. All divided by, now you can multiply that by 1, but go ahead and multiply by 1. That's not going to change anything on top. On the bottom, don't do anything. Leave the bottom as a bunch of factors. So I got 11, I got a 2x plus 5, and if I multiply now, I got an x minus 3. All right, now to continue going here, on top, I need something to cancel. I need a common factor. So, I realize on top I could factor out a 2. So if I factor out a 2, I get x minus 3. Double check my work if you want. And this is great news because I already see an x minus 3 on the bottom. That will be removed. So once those x minus 3's are gone, I can now go ahead and find the limit as x approaches 3 of my new function, which is really the same function, just written differently. And now I could re-plug in 3, and I will get my answer. So let's see here. When I re-plug in 3, I get negative 2 over 11 times 2 times 3 is 6. 6 plus 5 is 11. And 11 times 11 is 121, so I get negative 2 over 121. There is my limit. So don't be afraid of the fraction problems. They just take a little bit of time, but I trust that you guys can get them. They're not too bad, and you'll do great on them. So good luck on the tests. With this video, there's going to be some practice problems that cover these same exact problems I'm going over now. Watch this video, do those problems, and I think you'll be really well off on the tests.